Let me say something about discrete Sard in a delta set setting. Delta sets are Cartesian closed, they are a nice category, unlike finite abstract simplicity complexes or graphs where we don't have a Cartesian product which stays in the category. So finite sets would be fine. That's not a good place to do geometry. Quivers would have a Cartesian product, but also here it's not good to make geometry. We don't have a nice cohomology. So what you want to do is you want to be able to count nicely, and counting means have a cohomology. We need a Dirac operator. That's possible in delta sets. And delta sets naturally come in when you look at Sard. So here I again wrote down Sard in a special case when you have a real valued map on a simplicity complex. Then for almost all target values, for all except a finite set of values, we have always a manifold, a d-1 manifold, or it can be generalized to higher dimension, d-k manifold. So we have talked about this a couple of times. Here's an illustration. This is a Cartesian product of two simplicity complexes. However, we had to barycentrically refine it to get the simplicity complex. I did that since many years. It's actually the Stanley-Reisner construction, but it's not a Cartesian product. It's not associative. For example, if you multiply with 1, you get the barycentric refinement already. So in this case, when you have a function of the original, if you have a function of two variables, you have also to determine what you actually do. You have to lift the function up. So for example, here the colors red mean 1 and the colors blue mean 0. And on the vertices I could say what happens. That's actually on the vertices alone. And then I had to kind of extend it to the edges and extend it to the cells here, this is the barycentric refinement of this delta set. So that's and then now we have the theorem. We can apply the theorem, right? We have the level sets are always curves, closed curves, one manifolds. So these are closed curves. So I took here a torus. This is actually on a two-dimensional torus. I took randomly a few points, meaning randomly a map to Z2, and then we have a, so in this case you can do that also by mapping into a k-dimensional simplex, and then you get a codimension k manifold. We have seen that, and here you see just this. But we had to choose our lift. So the question is, can we do that directly on delta sets? Do we, or do we really need to lift it to a, a simplicity complex again to have that theorem? Now, I think it's possible, so you can do that also in a delta set. However, also there we have to make a little, some choice. So there can be a problem of overbooking of the cells. What happens is, so here, how did we define this level set? We define it as the set of simplices on which the function changes sign. So these are edges, or triangles. We don't have vertices on the vertex. There's no sign change, right? So there are only edges and triangles, meaning that you are in a delta set setting where you have to say these are kind of the edges are the zero-dimensional part of this geometry, and the triangles are the one-dimensional part of this geometry. So when you do that, you get nice manifolds. Especially if you have a graph of a function, and when you have a graph of a function, you can do that nicely, and you can define, you have a curve, right, which is then the graph of that function. So that's what we want to have in a Cartesian closed space. We want to have a notion of Cartesian product, so that we also have notions of graphs or maps from, these are maps, right? These are maps from y to z. So for example, already in the set of sets, when we have maps going from to 0, 1, these are actually kind of subsets. Subsets should be part of that category. We also have to have this is a little bit a weird kind of assumption which when you look up what Cartesian closed means, that we can rewrite a map as a graph. That's what we do in calculus, right? We have a map from R to R and we write it as a subset of the Cartesian product. So that's kind of what is here written in a fancy way using morphisms, homomorphisms. So it already fails when we take simplicity complexes, or if we take graphs. So we have not this nice notion, we want to have it, and so going to delta sets is really kind of a natural thing. I always avoided it early on, worked on on the Kunet formula. When you want to have a Kunet formula, you want actually, to use for the Cartesian, you want to use a simplicity complex again. Or if you take a graph, you want to have a simplicity complex of the product, which behaves naturally so that the dimensions add and all the notions, the cohomology satisfies Kunet, and everything has to be, as you have it in the continuum. Here, when you do that, a priori, kind of if you take it as a graph, and it's a one-dimensional graph, it's not a two-dimensional graph. If you take it as a simplicity complex, it's also, there are no triangles. So you could kind of refine it, or you could divide these cells up. So a priori, it's only a CW complex if you think geometrically, but it's better to think about it as a delta set, which you then can, refine, and you have then a simplicity complex. But in order to work nicely and efficiently, you want actually to work directly in the delta set. So I showed that in the case of cohomology, that's much, much, much faster to compute the cohomology here than to compute the cohomology here, because these are much, much more points. So this is a big improvement if you can directly work in the delta set. And we have seen that in SAR, right? If you look at these sets here which come in SAR, they are usually these manifolds which you get are surprisingly rich in a very small graph. You can get surprisingly rich geometries, but they are a priori just open sets. They are open sets, so only delta sets. They are not closed yet. So if you close it, you can close it by taking barycentric refinement. So that's what I wanted to say today.